Good afternoon, folks, and welcome to today's edition of the Iowa Learning Farms Conservation Webinar Series. My name is Ann Stout, and I'm a Conservation Outreach Specialist with the Iowa Learning Farms program. Appreciate you all joining us for today's webinar, and we're excited to welcome a new faculty member in the Department of Agricultural and Biosystems Engineering here at Iowa State University. Dr. Ryan McGehee is an assistant professor and he works in computational modeling, looking at a variety of aspects of natural resource conservation planning, climate change, variability, hydrologic and water quality, model development, as well as terrain modeling and flood prediction. So today we're going to be diving into conservation planning and specifically looking at the element of erosivity, looking at some of the established models as well as potential changes coming to those models related to erosivity and how that applies to water quality, watershed management, and planning. So we're excited to dive into the topic. Format of today's talk, after I finish the introductions here, I will turn it over to Ryan for about a 25-minute presentation. While he's presenting, you are welcome to submit any questions into the chat box here, and then I will compile those questions and relay them at the conclusion of the presentation. So please send those questions on over to me as the presentation is going on, as you think of them. So without further ado, I'm going to turn it on over to Dr. Ryan McGehee. Welcome.
Thank you. Thank you, Ann. And hello, everybody. Yes, so you can see the title slide today. I'm going to be talking to you about conservation planning and specifically this topic of erosivity. It's okay if you don't know what that is, I'm going to explain. But this is going to be a bit of a review, especially at the beginning, and then I'm going to start talking about where things are heading, and I'm going to give you some context around that as we move through the talk. So first, conservation planning. And now I'm not advancing slides. Okay, there we go. So how does conservation planning work, especially in the United States, for those that may not be familiar? Well, this is from NRCS, the Natural Resources Conservation Service. And if you're not familiar with them, they're basically responsible for implementing conservation planning in the US, and they use this 9-step process. This process is a bit intense, so I like to look at another figure that NRCS puts out that kind of boils it down a little bit more. And these are those same 9 steps broken out into 3 different phases. Phase 1 is a data collection and analysis. Phase 2 is decision support, and phase 3 for application and evaluation. When we're talking about modeling as it relates to this 9-step conservation planning process, basically in phase 1, we're having people go out to a field, collect some data, translate those to model inputs. In phase 2, we're actually going to be executing different model simulations and different configurations with your actual land or what you could do with your land. And then you will make decisions. And if anything is actually implemented, you will then compare those to the results that the model produced in phase 2 in phase 3. Okay, so that's the general overview. And today we're going to be talking about one particular resource concern. And if you're not familiar with the NRCS language, whenever someone goes out to visit a field and implement some kind of a conservation plan, they're always basing it around this idea or this terminology of a resource concern. So this is something that a landowner is concerned with. And one example of that is erosion. Erosion, and I'm showing 2 pictures here for a reason. This really got its start back in the 1930s in the Dust Bowl. You've probably heard that on some of these talks, if not very recently. At least at some point, and even in your primary education. So elementary school kids are introduced to the Dust Bowl and erosion topics. And this is what really motivated the formation of the SCS, now the NRCS. And you can see a picture here of the Dust Bowl, and then a picture on the right that shows that this is still occurring today. And I just like to show this because these problems haven't gone away completely. They've reduced in severity and frequency, but they still occur today. And I just want to show some of the variety of different erosion problems that we see. So here on the bottom left, you can see wind erosion occurring on a field that's fallow. And these are kind of close to home for us here in Iowa. This picture in the bottom left is of Kansas. I actually don't know where this one is in the top left. This one's in Tennessee, showing some sheet and rill flow and erosion in a cornfield. In the top right, we have a small classical gully that's formed in South Dakota. Here on the bottom in the middle, we have rills. This is not cropland, but it's still off of a construction site and is a good picture that's from Ankeny. And in the bottom right, this is not in the US. This is a picture from Bangladesh showing mass wasting. So all of these processes together are what we are trying to reduce or eliminate from our different lands that we want to conserve soil and water from, and nutrients as well. And the big question is it working? Are our conservation planning processes and practices working? And to answer this question, I'm going to point to the National Resources Inventory. This is a database or an assessment that is put together by the NRI every few years. The most recent, and I checked this morning, was from 2017. And you can see from 1982 to 2012, which was the last figure that was updated, and 2017 I have fixed here on the right, so you can kind of see this is the most recent picture of where we are today compared to where we were. And the short answer is, over the last 40 years, yes, we've seen a drastic reduction in sheet and rill erosion rates. But what does that mean exactly? And I also have another figure here just to emphasize the point. So if you don't like moving pictures, this helps emphasize that a little bit more. This breaks down the NRI results I just showed you to erosion on highly erodible land, which is in red, and erosion on non-highly erodible land, which is green. And you can see we've tackled a lot of the non-highly erodible land issues, especially in Iowa, but we still have those highly erodible land issues that remain. And again, this is according to NRI. It's not updated every year. And, there are a whole lot of questions that go into, okay, how did you come up with this? But using the same methodology, we can see that things are improving, but there's still some problems that remain. So question, why do some of those problems still remain? Why are we still seeing erosion? And I don't know if you're like me, but I drive around after a storm. I still see muddy streams. I still see ephemeral gullies forming on different fields and farms around Iowa. And the question is, why is that happening if we are implementing conservation at scale? And no, not everybody is, but even on the ones that are, why do we still see that? And this is a two-part answer. So part one, I want to point out, not every erosion process is included in conservation planning. So I have here all three of the big ones: wind, water, and translocation, and the different processes underneath each of those. So you have under wind, suspension, saltation, and creep. I'm going to show you some pictures of that in a second, or a picture of that. And then underwater, we have 6 different processes: splash, sheet, and rill. You just heard me say sheet and rill erosion. Sometimes splash is lumped in with sheet, and people will still refer to it as sheet and rill, even though it's including that smaller practice. And then there are these ephemeral gully, classical gully, and mass wasting. We usually don't address those, and I'm going to show you that later. And then we have translocation. Translocation is I'm actually moving soil, but it's not being moved by wind or water. It's being moved by humans, by anthropogenic action, either through tillage or root crop harvest. So if you're farming potatoes and you are harvesting those, you're actually picking up soil and moving it too. So both of those processes have to be accounted for as well. And that should raise a question immediately, because some people would say, hey, wait a minute, I know that tillage is an input for some of these water erosion processes. You are not wrong, that is correct. We also have to include the effects of tillage on water erosion processes, but that is not the same as when I actually do tillage. I'm moving the entire layer of my soil some small amount every time I make a pass with a certain direction and velocity. So we'll talk about that more later, but I do want to point out that the models that are used for conservation planning, there is an official model used by NRCS for wind, that is the Wind Erosion Prediction System, and for water, that's the Revised Universal Soil Loss Equation version 2. And there is no model that is adopted or used for translocation. So this is something we totally do not include right now. So for wind, if you're not familiar with those 3 processes, I have them shown here. I'm not going to spend a lot of time, but just suspension. Generally, these are small particles. Your medium-sized particles, they can bounce along the surface. That's called saltation. And then your larger particles, they're going to be moved by rolling over the surface. That's called creep. So WEPS is a model that accounts for each of these. Russell 2 is another model, and it is used to account for splash, sheet, and rill erosion. It does not support ephemeral gully, classical gully, or mass wasting. So I just don't want people to be confused. These three processes are not being included in any kind of conservation planning model that we have available to us right now. But splash, sheet, and rill definitely are. And those are lumped into a single output, usually called hill slope soil loss or hill slope sediment yield or hill slope detachment, something like that from various models. Okay. And then that is what you're actually seeing. Now, the NRI report, it is accounting for these three processes, splash, sheet, and rill, even though it's only called sheet and rill. I just wanted to make that clear for everybody. And then we have that last one I talked about, translocation. And just so that you understand what this is, translocation is I'm actually moving my soil, and then that soil, after it's been moved and disturbed, can be picked up by water and carried further. But the process of tillage erosion is different from water erosion in that I can accelerate the natural process of water. So here's a natural landscape on the top where I've got very thin soils on the summits and very thick soils on the slopes, because over time water erosion has redistributed that soil as such. But tillage erosion actually accelerates that practice, and I will get a greater cut on my summits and a greater fill on my toe slopes. And again, we do not account for this, and here's a nice picture showing this issue in Canada where a lot of this work is being done to quantify tillage erosion. So just to summarize in a single slide again, these are the processes that are included and accounted for in the officially adopted models at NRCS, and the ones that are grayed out here are not included. So you can see we're accounting for several processes, but not all of them. So if you're confused about why are we still seeing erosion as a problem across the country, well, here's a big reason. Part two. So some model inputs of even the ones that we are including still need regular updates. So these are things like something might have changed that was assumed in the model in the beginning. For example, climate. Climate is something that changes over time, and we have to account for any of those changes. They can be small, they can be back and forth like natural variability, or they could be long-term change driven by greenhouse gas emissions. So the model that is used by NRCS, Russell 2, is based on a fundamental equation known as the universal soil loss equation. And this is how the universal soil loss equation looks and what all it accounts for. So you have this basic relationship, and I'm going to annotate this slide so you can see, of A equals RK. And this is known as the driving relationship behind USLE. And then you have these four modifying factors for the slope length, the slope steepness, the cover and management, and then the practice factor, if you are to have those. I'm going to focus on the A equals RK relationship because this is what we're expecting to have changed over time. And I just want you to understand how it was formulated. So in the USLE, we collected soil loss, average annual soil loss, which is A on the left, and then we calculated, based on observed precipitation data, the erosivity, or R, over time. And as each year would pass, we would notice some wet years, some dry years, some low intensity years, some high intensity years, and you'd get some kind of a data spread that looks something like this. And then we would just regress that. And the regression through here and the slope of that regression is where we get our K factor in that equation. So that should be all I need to annotate so that you understand how the USLE works. And I'm trying to advance the slide. Oh no, my annotations didn't go away. So let me go back and erase that real quick. Sorry for the pause. I wasn't expecting it to keep the annotations. Okay, now we can move on. So USLE was developed in it was developed over the period from 1930s to the late 1950s. And I just have some photos here because I enjoy showing these, but this is Hugh Hammond Bennett that was the chief of SCS for some time with some of the first plots that were established in 1930. These are two technicians at Purdue University when we had a very large amount of USLE plots in that area in Indiana. I cannot remember the exact number, but you can see it trail off in this photo into the distance. And each of these are just huge. I'm going to show you the scale in a second. And this was in the 1950s. If your video is blocking here, there's a 1950s car you can see. Then we have in the 1960s, the plots evolved a little bit. They got a little bit smaller. So these were small because they were, at the beginning, there wasn't much money and they didn't know what they were doing. So these were kind of pilot, but these were huge plots that were used to develop USLE, and things have gotten smaller since then in the 1960s. And this is, I'm blanking on a name, famous scientist here shown, but again, picture from the 1960s of some erosion work on plots. And this is the kind of information that was produced in the USLE data that was recorded back then. And I'm showing you an example from 1937, April 3rd. The important thing here is that this precipitation information is not recorded on regular intervals. Now, in this example here, it happens to fall on 15-minute intervals, but they're not all like that. Some of them do not. For example, you can note the runoff over here does not. And in several other examples in other locations and around the world, they are not. And I'm going to bring that point back up to you later because that's very important, that they do not fall on regular intervals. And this is a graphical version of what you just saw in that table. And to point out, this precipitation information is recorded at non-regular intervals. And this is very important. And this is the cumulative information, which then produces these intensity hyetographs. You don't have to know what that word means, but just know that this is a very critical part of getting the erosion prediction correct. And the USLE data was related to erosion off of those plots with a correlation factor greater than 0.9, which is exceptional work. It's very hard to get that kind of work today. And I just want to provide some reference because these are two sets of pictures from a recent study that I did with model development, just to show you that we don't work with such large plots anymore. This was a study from the 1980s, and this is a study from the late 2000s, before the 2010s. So these are very small plots. As you can see, these are very small 1-inch PVC pipes, and our plots are much smaller than they used to be. So this is just helping you understand the scale here of USLE versus what we're doing today with modern data. I'm going to clean this up so you can see it more clearly. So these were the plots that we used in the 1980s, and these are the plots that we're using right now. And this is what was used for USLE. So these are massive plots. They take a lot of time. To give you kind of an idea, it takes about 30 minutes to an hour in an assembly line process to set up many of these little plots under different treatments. So when you see how many plots that they had at this scale, you should just know that that was years and years of work. And I think I added it up at some point that the total cost over the 20-something years was something around $600 million to $1 billion in today's currency for replicating this data. It's huge. So I want to go back and annotate this just briefly and explain to you one more thing, which is that A equals RK relationship, so A, R here, for USLE, it was done on an average annual basis. And the only difference between USLE and there are a few other differences, but the main difference in formulation is that this relationship was calculated every day of the year instead of every year. Okay, and then you would take the average of all the January 1st in the record and all the January 2nds in the record, and that's how you would obtain your A equals RK relationship. So there's the big difference between USLE and Russell 2, just so that you're aware. Why is that check mark there? Okay. So this is what is used in Russell 2 currently for erosivity, and this is how it changes across the United States. Something I'll point out that's very important is that this is from 1960 to 1999. So the climate that we are still using today in conservation planning for the US is based on this period and therefore the average of that period is around 1980. So our mean climate data that we're using for conservation is 44 years in the past. That's where the average of the data is. So that is a significant statement for you to understand. And I'm gonna show you how these maps are made and how they are changing in the future. Erosivity is sensitive to precipitation characteristics. So that map that I just showed you is representing the concept of erosivity as a number, and I'm going to explain what that is if you don't know. So what is it? Erosivity is the capacity of rainfall to cause erosion. And we use a numerical index called the erosion index to represent erosivity in all of our USLE-based models or applications. And there's a general procedure that we use to calculate it. The important things to remember here are that there are really just two things that are being multiplied by each other. It is the kinetic energy here, step 2, and number 3, maximum 30-minute intensity of a storm. And when we multiply those two pieces of information, then we can come up with the erosion index. And we can sum it over a period of time and represent different periods. This is what that looks like. So kinetic energy and how it changes with intensity in the US. So this is 0 millimeters per hour. This is 250. So it corresponds from 0 to about 10 inches per hour. So that's a big storm. We do see those storms. And the largest I've ever seen, which I'm not sure if this is necessarily right, but the largest I've ever seen come off of a sensor in one of these national databases is about 46 inches per hour. So that's extremely rare. It was one event out of 1,000 stations over 20 years, but we don't see intensities that high. Usually they're between 10 inches per hour and 0. And you can see how the different relationships, they all fall kind of in the same range. We know that it's a logarithmic relationship. Some of these are technically polynomial, so the McGregor-Muchler one, but they all follow this same general pattern where your kinetic energy increases drastically with your intensity and with your raindrop size initially, and then it levels off very quickly. You can see the Russell 2 relationship here. And we can see how this varies for a storm. So that was just the kinetic energy of a given instant in time, but we have to calculate this for an entire storm. So once you do that, and again, looking at that same range, so 0 to 10 inches per hour for a 30-minute storm in the US, what kind of kinetic energy comes off of those different equations? As you can see, they are mostly proportional with the intensity and don't disagree. But the 30-minute constant intensity and the erosion index, which if you remember is the kinetic energy times the 30-minute intensity, maximum 30-minute intensity, then we get an exponential relationship. So now this is what I was pointing out when I said erosivity is sensitive to these inputs. So if our precipitation changes by 10%, yes, we're going to get more erosion. If our intensity changes by 10%, we get a lot more erosion. Okay, so or conversely, if our intensity goes down 10%, then we'll get a lot less. So it's just a very sensitive parameter. And one other final point about this, the erosivity relationship to erosion was based on breakpoint precipitation data. And I know you don't know what that term is, so I'll explain in just a second. But this is what a breakpoint gauge looked like. And this is what, in fact, they used. So all of that data that I just showed you was being collected, and it looks like this. So it's a continuous data set, whereas our modern precipitation data sets, it's just giving us basically a point here and a point here and a point here, whereas this gauge gives us a continuous line of data. And then that is used to convert to periods of representative rainfall. I'll explain that again in just a second. You can see here that it's based on what's called a floating pin and pointer gauge type design. So the rainfall comes in, and based off the flow rate here, the buoyancy force of that water is going to push this float up, and the pin allows that captured rainwater to pass through at a certain intensity based on its buoyancy. Then that is connected to a lever here, which is connected to a rotating drum, and the rotating drum is where we get these lines coming off the gauge. So this is a completely different amount of information and a totally different quality compared to what I'm showing here on the top right, which is a very common weighing bucket gauge where we have a scale and we're weighing how much water is coming in, and we just report the number every few minutes or so. So if you had never heard of breakpoint data before this is a summary of that. So breakpoint data is a time series whose breaks correspond with actual breaks in reality. You saw that continuous data set that I showed you in the graph versus fixed interval. This is the more common type of gauge, and it's cheaper. It's a time series whose breaks correspond with regular time intervals, meaning every 5 minutes or every 10 minutes or every 15 minutes. And the point I wanted to bring out was that Wishmeyer and Smith, this guy here, and Smith here, they are the ones that establish the relationship of erosivity to erosion off of plots. And they use this data, breakpoint data, not fixed interval data. So I want to show you just a little bit more in depth with an example. This is a very common hypothetical example taught in classes here when we teach about erosivity. So this is breakpoint data. You know that because the duration is not fixed. You see 20 minutes, 7 minutes, 9 minutes, 14. If it were fixed, it would say 5, 5, 5, 5, 5, or 15, 15, 15, 15, or 10, whatever duration, as long as it's repeated. So this is breakpoint data because it's changing in duration. And when we're recording depth at the different precisions that our gauges are designed for, low and high precisions, which you can see, it's not very different, or it doesn't look very different. We end up following the line pretty closely, and we end up at the same point in this example. And you can see the different breakpoint is the black line, and the different fixed intervals, 5, 10, 15, and 30 minute, are in the different colored lines. When we start looking at intensity, though, now you start to see a big departure from our breakpoint data, the black line. And this is what is so critical for erosivity. If you recall, I just showed you how sensitive erosivity was to intensity, and now I'm showing you that the different gauges that we're using for our technologies, they impact that. So when we interpret this in terms of erosion index, we have low precision and high precision again. You can see a very clear bias introduced by the resolution of our gauge interval if we use these fixed interval gauges. So I have here 5, 10, 15, and 30-minute data, and this is a large storm. This effect is even larger for small storms, okay? It's larger for small storms, it's smaller for large storms. This is a 3-inch event that occurs in about 1.5 hours. So it's, what would that be? 4.5 inches per hour. So it's a sizable storm. And then on the right, you can see that increasing the precision of the gauge improves this issue, but it's still there, right? So this is better. It's good if we're using high precision data going forward with 15-minute data, but it's still an issue of there's this gap between breakpoint and 15-minute. So then another question, how has erosivity changed over time? And I'm going to put an asterisk here because I'm wrapping up the talk. But this is all of this that I'm about to show you is according to 15-minute fixed interval data. So this is not according to breakpoint data. The results would be different. But we use 15-minute data because there are not so many breakpoint stations out there, and we have to use something like this. So here's the original map in 1976, and I apologize, this is in English units. If you want to convert, you would multiply these values by 17.02 to get it into the SI units that I'm about to show you on the next plots. But you can see that generally in the southeast, it's the greatest, and it moves over towards the west coast and the northeast and decreases. And then there's an exception in the California and Washington, Oregon Valley here that you get an increase in erosivity on the mountain sides, okay? Then this is the map I already showed you with Russell 2. This is what is currently being used for conservation planning today in the United States. You can see the data type is 1960 to 1999. It is using a mixed amount of fixed interval data, but primarily 15-minute data. The data that is not 15-minute would be from 1960 to 1970, and after 1970, virtually all the data is 15-minute. The precision is a low precision, 2.54 millimeters, and it's using a not recommended version of kriging or a method of kriging that goes all the way to the coast. As you can see, you do not capture that valley issue between the mountains. This was a more recent publication that was actually global by Panagos. So this is a European individual that works with erosivity. You can see the time period here is more updated, so it's more recent. It's still fixed interval, it's 5-minute, and the precision is a higher precision. So you would think you would have better results here. They use a Gaussian process regression here, and you can see the biggest thing I wanted to point out from this map is that you can start to see the West Coast valley and mountains issue with erosivity again. You can see a map that I produced in 2022 using 15-minute data from 1970 to 2013. This is fixed interval, 15-minute data. So this is largely the same as the Russell 2 database. And in fact, it is still the recommended input for Russell 2. It is low precision, 2.54 millimeters, universal kriging. So that's a very different method than ordinary. You can start to see the coast very well. And we've even tested this for some small areas. For example, in Tucson, which I think is down here, Tucson, Arizona, you can actually see the increase in erosivity from the city of Tucson to the top of Mount Lemon. I'm not sure how to say the mountain there. But anyway, I worked with the Southwest Watershed Research Center to see if these values were realistic for even those arid areas. And this captures about 75% of what they were seeing, whereas prior maps didn't do anything in those areas. So this was a really good accomplishment. You'll see 2 dots here. I want you to keep that in your mind. So 1 dot in Mississippi, 1 dot in Massachusetts. I'm going to come back to that when I talk a little bit about validation. So what is the difference between the existing map and what I just showed you, which is one of the more recent ones for the US? And here's the absolute difference in erosivity. This doesn't have a whole lot of meaning to most people, so I'm going to show you a relative difference on the next slide. But I want you to see that largely not huge changes in erosivity. There are big changes in the map, especially out west, where you see that difference in the interpolation method, and you see some differences in the southeast. But you keep in mind that these were already very large values of erosivity, so those actually are not that large. So when we're talking about relative difference, then you can start to see a much, much different picture. And in general, erosivity across the US has increased substantially since the mean before of 1980 till now. And the new data set, like I showed you, was from 1970 to 2013. So just updating for that period, we see a substantial increase, 30 and 40% across a lot of the Midwest up here, and even 15, 25% in other places that are not the Corn Belt, if you will. You see some differences out west that are extreme. Again, these were because of the interpolation differences out west that are largely linked to elevation differences and the fact that a lot of storms were being omitted that were small storms and considered insignificant for erosion. So when you have very, very little erosion and you see a small increase in erosion, you can see doubling of it, and it makes this map look worse than it is. It's not a whole lot of change out here, as you can see. So this is why I have the absolute difference map with the relative map. I do want to point out a recent discrepancy. I believe that I should be transparent when people may disagree. And so here is one of those that was published just last year, 2023, by the same author that published the 2017 paper. And they actually have updated values in the US and revised them down. Now, I'm not exactly sure why this is. It does seem to conflict with the consensus of other authors around the globe, but in the spirit of transparency, I think I should make everyone aware and you should know where to look if you were to want to investigate further. There is a new paper that is accepted and is going to be published. It is in print right now, 2024. This paper looked extensively at erosivity around the world and compared to different studies. So you can see some of these. I'm not sure if you can see at the top because I have a menu bar there, but at the top it talks about the different studies that were the Panagos studies from before. So here's the 2023 Panagos study, this column here for different locations around the world. And then these are regional studies, and that's where you saw the other map that I showed that I produced in 2022 here. So you can see how the satellite product compares to that. So this is something that's on the horizon too. And then this is the big one, and this is the one that everyone would want to pay attention to. This is the paper that will have the largest influence on the official NRCS Russell 2 results. It is forthcoming. I cannot share any details about what is in the paper until it is actually published per an agreement with the authors. But these are the authors and these are the analyses that are included. And you can see it's largely consistent with the historical map and the new map in 2022. The big difference is that my map does not exclude 50-year events, whereas this map will exclude 50-year events. So that's all I'll say there. And I do want to leave with a question in your mind. So last two slides here. If we update erosivity using 15-minute data, is it similar enough to breakpoint data, which is used to develop the USLE and its sibling models? So you'll recall that I showed you how we've used 15-minute data to prepare the erosivity input for Russell 2 and USLE. I've shown you how erosivity is sensitive to intensity changes, and I've shown you the difference between 15-minute and breakpoint data when it comes to both intensity and erosivity. Now, all of the maps I just showed you, you remember I showed you the asterisk, it was showing you results based off 15-minute data. All of these are based off that. None of these are looking at the breakpoint data, which is what was originally used by Wishmeyer and Smith. And I think it's a significant risk factor. I also told you, if you remember, there were 2 points on the map that I showed that were in Mississippi and Massachusetts. The reason that that concerns me, and this is available for anybody, and I will annotate this just briefly so you can see better. So here is our Mississippi site. Here is our Massachusetts site. Note the time periods. So the time periods don't necessarily align, and that's a factor. But I want you to note the McGehee 2022 study, 1970 to 2023. We were below the benchmark in both of those cases, and we did not remove 50-year storms, and we corrected for gauge differences using the same rules as Russell 2. And I consider this a major risk factor for all of our conservation planning of water-based erosion. So if you recall, Russell 2 supports or predicts splash sheet and rill erosion. And the erosivity that we're using to drive it, which is here, this is the current 2008, is below our benchmark breakpoint data that we do have. And even when we updated that information, we were still below. With that, I can erase my annotations. I'll be happy to take any kind of comments, questions, or discussion. And thank you so much for your attention.
Excellent. Thank you, Ryan. And folks, feel free to type any questions that you have in the chat box at this time, and I will relay those. We have had a handful of questions come in, and appreciate the really interesting presentation, especially diving into some of the history of the development of these models and looking at the different plots. Very fascinating to see. One clarification question. This one went back to the beginning when you were talking about the different types of erosion and the different models that went with those. So you mentioned with translocation that there are no models. So is that there are absolutely no models at all, or are there no specific models tied in with
Right.
tied in with specific initiatives like the NRI?
Yes. We do have models actually, but they're not adopted for, so here's one, and there are at least three that I know of, but one is the directional tillage erosion model, Deer Tillum. So this model exists, but if you know, it is not adopted by NRCS. It is not a model that is used for modeling and predicting translocation issues. And it's often one that gets lumped in with water. People tend to get these two processes confused, and that might be why there is no adopted model, is just because people aren't aware that it's occurring. So this is in part to try to educate people to help them understand that that is a process that is occurring.
Sounds good. Okay, how does wind erosion factor in? Less rain, more wind erosion, kind of what's the relationship?
Yep, the relationship definitely is that when you are in lower rain, more arid climates, from 0 to about 300 millimeters per year of rain, so that would be almost 1 foot of rain per year, 12 inches, right? So 12 inches of rain or less, you're going to be primarily driven by wind erosion, at least according to ARS research. So maybe there's some location out in the world somewhere under 300 millimeters that still has significant water erosion. We don't know about it. So yeah, that's where your wind is going to occur. I do not have numbers in terms of magnitude. So if you're looking for a tons per acre per year, I do not have extensive experience with any kind of WEPS modeling, actually executing WEPS or any other of the wind models. So the one prior to that would be the wind erosion equation, WEQ. I have not run those, and I don't know the tons per acre or tons per hectare off the top of my head.
Sounds good. All right. So for farmers and landowners or for, NRCS conservation professionals working in the field, what do you see as the management implications of this increasing erosivity that is being experienced across the country?
Right. So the biggest implication I see is that you're going to not be controlling splash sheet and rill erosion like you may be expecting. And because you're not controlling that erosion and runoff, because that's a factor here as well, then you're going to be generating more channel erosion later. Because if you're not controlling at the source, you're going to have that issue build up as you uh, that issue will continue to build as you move further down in the watershed, right? So generally, we're talking about some very upland area. We're not talking about in the channel. Uh, but if you're not controlling upland areas, and if you've got this significant underestimation, you saw 30-40% is what I say in my map versus the prior Russell 2 map. And I'm 20% below the benchmark for erosivity in the two places we looked. So that's 40 to 60% in the Midwest. That's a huge factor. And then you have to remember that that was just splash sheet and rill erosion. That was not wind and translocation, which supposedly we're keeping up with wind, but we're missing 3 of the water erosion processes and tillage translocation. So all of that is why we still see significant erosion problems in our watersheds.
All right. What do you see as any expectations in terms of timeline with revisions to the Russell 2 model modifications once that MUM paper is published?
Yeah, the mom paper will come out in 2025. I don't think it'll be done before December. And after that, I cannot speak to the internal process of NRCS's adoption. I will point out that this is a moving window time period. So there will no longer be, as I understand, a static database, but there will be every 5 years, you're getting updated climates. So this will now start to move with our climate and will become a more dynamic product. There are places in the US that did go down in erosivity. So this is not all bad and everything's getting worse. It's not that. But some places do, and some places get better. The climate's changing in their favor. So that is a important thing to keep in mind. And no, I will not know the official numbers until it comes out just the same as everybody else.
Sounds good. So for conservation professionals that are working with farmers and landowners, and or just for interested folks, what scale are these are on what scale are these models typically being applied, like in the conservation planning process? Is it a single field, or what's the size we're looking at?
Yeah, it is up to the landowner. That's the correct answer. But a landowner usually is only concerned about one part of my field even. And the terminology that I frequently hear from NRCS are hill slope. So a hill slope, if you're not familiar with that definition, let's see if I can find a blank slide to annotate on. So a hill slope is going to be a continuous surface that is monotonically decreasing. What that means is that it never goes back up like this. So if I go back up, this is not a hill slope on the right. This would be a hill slope from here to here, and then this would be a hill slope from here flowing this way, and then this would be a hill slope flowing that way. And obviously the water that accumulates here would have to go into or out of the page as I've drawn it. So it's a 2D, not a 1D problem. So the models are being applied at the hill slope scale. They will represent this slope right here in either WEP or Russell 2. So Russell 2 is the official model. If a landowner wants to use what's called a supplemental planning tool, you can use alternative models to estimate your erosion to see if it's more or less favorable for you. But you would still be doing the same process where you're looking at the slope, providing all the inputs that you have on that place of concern, wherever your erosion problem is, and then you'll see what the model predicts for erosion for that problem. And then, as I mentioned in phase 2, you'll look at different opportunities. For example, if I wanted to consider going to a different tillage system, or if I wanted to consider a different crop rotation, then I can look at those.
Sounds good. All right. And another question, what about contouring?
Contouring, specifically, what is the question? They are included in the models.
They are. Okay.
Yep.
But
If
it is
if that's the
currently
question,
factored in.
yep. Contouring is definitely factored in. Terracing is factored in. Some models lend themselves better to terracing than others. Let's see. Yeah, I mean, virtually any agricultural management practice, structural or non-structural, is covered by at least one model. I'm actually unaware of any that are not.
Okay, and then this is kind of a related question too. So, history of diverse crop rotations and manure applications. So that typically improves infiltration and holding capacity. But farmers don't seem to get credit for this in Russell 2 for their past practices. What
Yep.
are your thoughts in terms of how that can better be factored in, looking at soil health, organic matter?
Yeah,
Just
composting needs to be factored in, especially these tools, especially since Russell 2, you'll hear from even their own modeling group that Russell 2 is a long-term modeling system. You have to have a lot of data to be able to even use it, and then you're getting average annual results back. But those average, so it's a hard place to be because yes, you're long term and that you want to look at those average annual soil loss results, and that's the only place the model's valid is when it's applied long term. But you also have these very dynamic issues, like if you start applying animal manure on your field, it's going to compost and build up organic matter, and that should be accounted for over time. And in fact, there are models that do represent that, but that's not one of them in the official NRCS model, and that's all I really have to say about that. But yes, I agree with you. It should be included, and it is not.
okay. And then finally, I'm going to take this as our last question of the day, just for the sake of time here. But thoughts on T values that have been currently assigned by soil and water conservation districts, comparing that with your data.
Yeah, T values are a value that indicate if you have an acute soil loss problem. And that's the exact language that's used. So if you are below T, it does not mean that you are a sustainable farmer. It just means that you don't have an acute problem. And no one has really come up with at least a number that everyone agrees on. I'm not sure what that would be, but it's quite a bit lower than what your usual T values are. I've seen 3, I've seen 5, depending on different soils. I haven't seen many that are much lower than 3. Maybe there are some that I'm just not aware of. But I would point to this factor here. Right now, T is being calculated only using these processes in black, not using any of those in gray. So even if you are under T for those in black, you could be violating T for those in gray, but we just don't account for it yet. So that's a significant factor. Maybe T doesn't have to move that much if we include these other processes, but we've kind of been getting away with using T values that are supposed to be representative of, okay, if I'm below this, I don't have a real problem, but how can I say that if I'm only looking at a few of the processes occurring? So it's an awkward place to be in. That I think that's where the question was getting at. It's spot on.
Great. Sounds good. Well, thank you everyone for all the questions. Like I said, I know I wasn't able to get to all of them, but wanted to hit on as many as we could in the time we have. And Ryan, would you be able to pull up those last couple slides just so we can preview our next webinar and what's coming in the series? Perfect. All right. And so if you watch today's webinar to earn a continuing education unit, a CEU, please send an email today by 5 o'clock to Alena Whitaker, ALENAW at iastate.edu. The information needed is listed on your screen there. So include your name, the name you used to watch the webinar, if that's different, and then of course your CCA number, and we will take care of getting that submitted for you to get you your credit. All right, next slide there. We'd appreciate if you haven't done this before with an Iowa Learning Farms webinar, we'd appreciate your participation in this voluntary demographic survey, which is a part of USDA funded programs. So you can find that online at iowalearningfarms.org/survey, as well as if you're feeling tech savvy, you can scan the QR code there on your screen with your tablet or smartphone and complete the demographic survey that way. And then next week, same time, same place, next Wednesday, October 2nd, we're excited to welcome back Dr. Emily Heaton. She's currently at the University of Illinois and was previously here at Iowa State University, but she will be sharing some really exciting information on advanced biomass crops as tools for regenerative agriculture. So that definitely promises to be an exciting presentation as well. So next Wednesday, October 2nd, same time, same place with Dr. Emily Heaton. And then finally, I know we've gotten a few questions in the chat already about today's presentation. It will be archived. We'll have it up online this afternoon at iowalearningfarms.org/webinars, as well as up on our YouTube channel as well, where you can find all of our today's presentation as well as past presentations in this series. So today's presentation will be up later today for everyone to check out. So with that, I know there's I'll just want to pass it around, many kudos in the chat. Awesome presentation, awesome webinar, learned a lot and how to apply it in practice. So appreciate everyone tuning in. And Ryan, I'll turn it over to you just for any final words, final thoughts.
No, I don't have anything to add. I'm willing to give this presentation away to anyone that wants it if you just email me. But thank you all for your attention and your questions. I enjoyed giving this talk.
Wonderful. Thank you so much. And everyone have a great day.